So in our study of one-dimensional motion, we've moved on to the study of free fall. When you drop an object, it moves in one dimension, from wherever you release it straight down toward the ground, and it moves with a constant acceleration. And that resulting motion, when gravity is the only force affecting the object, is known as free fall. In fact, that's worth writing down. You should certainly include this statement in your notes, that free fall is the motion that results when the only force acting on an object is gravity. I want to drive a point home here, so I probably should add something to that statement. Let's see, once again. Free fall is the motion that results, comma, when the, how about this? One and only force acting on an object is gravity. So for example, if a block is sitting on top of a desk, well, certainly gravity is acting on that block. There's a force of gravity, which we can represent, just as a downward arrow, right? We can picture this downward pull as being the effect of gravity. But at the same time, due to the fact that this block is resting on the surface of a desk, the desk is pushing back up on the block just as hard as the earth is pulling down on the block. So we can give some names to these. We can say this is the force of gravity. We'll say this is the force from the desk. And if those forces are in opposite directions and of the same strength, they tend to cancel each other out and it doesn't move at all. If you drop something like a leaf, and you let that leaf fall toward the ground, then certainly the force of gravity is pulling downward on that leaf. There's an upward force. Now in this case, the upward force is not as big as the downward force, so they don't cancel each other out. But as gravity pulls down, air resistance pushes back up. So this would not be an object in free fall, just as the block on the desk is not free fall. So just because gravity is a force that's acting on an object doesn't mean it's in free fall. Gravity has to be the one and only force that's acting for an object to be in free fall, which means free fall covers more than just dropping an object. So if an apple were to fall from a tree, sure, it starts from an initial velocity of 0 and it falls straight down and then either hits the ground or hits Isaac Newton on the head, whichever. That's an example of falling with air resistance, right? Even an apple falling from the tree encounters a slight amount of air resistance. So free fall, there aren't many good examples of an object in free fall on the Earth. In some cases, the downward pull of gravity is so large in comparison to the tiny little upward pull or push of air resistance that we say the air resistance becomes negligible, and we say for all practical purposes the object is in free fall. But to truly get something in free fall, it would have to fall through a vacuum. Or here's an example of free fall. The radius of the Earth is about 4,000 miles. That's the same thing as 6,400 kilometers. The Earth's atmosphere only extends another 200 miles. So I think even here I've exaggerated the height of the atmosphere. So when we put an object into orbit, a small part of the energy is just to get it up high enough that it gets out of the atmosphere, but the majority of the energy is to project it sideways with a great enough speed that as the pull of gravity toward the center of the Earth wants to pull it down, it has an initial velocity that's not equal to 0 projected sideways. So as it tries to follow based on the law of inertia, this dashed line path, but at the same time, the force of gravity is pulling downward toward the center of the Earth, it causes the object, if this speed is just right, to be in free fall around the Earth. Again, gravity is the only force that's acting, but the motion certainly isn't in a straight line, right? So free fall, notice the definition doesn't say, we didn't have to add in here, free fall is the straight line motion, because it's not. The motion that results doesn't have to be in a straight line. It could be circular. Objects in orbit around a planet are in free fall. It could be in a straight line. It could also be in a parabola. If you kick a soccer ball across level ground, so that the initial velocity points at some angle, then the path fallen is parabolic, and at any point, when the ball gets right here, gravity is pulling straight downward. When the ball gets here, gravity pulls straight down. When the ball's at the highest point in its trajectory, gravity's pulling straight down. And there's no other force acting on it if we're willing to say air resistance is negligible. So projectile following a parabolic path, a satellite that's in orbit, or an apple that falls from a tree are all examples of free fall, because they're all examples in which either gravity is the one and only force acting, or the force of air resistance is so small that we can ignore it and pretend that gravity is the one and only force that's acting. Why don't heavy things fall at a greater rate than light objects? So what if we were to take a hammer, for example? And drop it next to a feather. Well, we know that the hammer is going to fall faster and the feather is going to fall slower. And you can make the conclusion that the hammer falls fast because it's heavy and the feather falls slowly because it's light. But then I would challenge you, like maybe feathers just have an inherent slowness to them, and hammers have an inherent fastness to them. So I want you to imagine this compound object. My compound object is made of a feather that's been tied to the hammer. Now, of all three objects, A, B, and C, which one falls the slowest? I think you'd all argue the feather. If we make the presumption that feathers have inherent slowness and hammers have inherent fastness, then you might guess that object C falls slower than the hammer itself because the feather's slowness slows it down. But others would argue, now wait a minute, by attaching the feather to the hammer, you've made an object that's even heavier than the hammer by itself. And if heaviness is what gives an object a fast motion, then the compound object should be faster than the hammer alone. So obviously, considering that the rate at which things fall is a function of their mass leads to contradiction. Instead, if we can imagine dropping something in a vacuum, then what if I were to drop a bowling ball versus a ping pong ball? Isn't there a much larger force of gravity pulling on a heavy object like a bowling ball? and there's quite a bit less force of gravity on the ping pong ball. So with greater force, shouldn't there be a greater acceleration acting on the bowling ball? There also happens to be more inertia. I think I stated in the first video lesson for this unit that inertia is synonymous with mass. So this bowling ball, if you were to drop it from a state of rest, has a very large desire to stay at rest. The ping pong ball also has inertia because it has mass, but it doesn't have as much mass. So it doesn't have as much of a desire to stay at rest. It has some, but not as much. So the idea is it has a smaller force, which is all that it takes to overcome a smaller amount of inertia. The bowling ball has a whole lot of inertia, so to get it to accelerate at the same rate should require a much larger force. In the end, this is all explained by way of Newton's second law of motion that says the acceleration of an object is equal to the net force acting on it divided by the inertia of the object, or the mass of the object. Now, when gravity is the one and only force acting, when an object is in free fall, then the one and only force is the same as the sum of all forces, and one shortcut to finding the force of gravity is to multiply the mass of the object times the value of free fall acceleration. So if the acceleration of the object is equal to mg divided by m, then the m cancels out, and an object in free fall has an acceleration equal to 9.8 meters per second squared. So all objects should fall at the same rate when dropped in a vacuum, and I have a video demonstration of that you can watch after this lesson. And also, the astronaut, I think his name is David Scott. No, that's the guy from The Office. Michael Scott? Oh, I'm confused at this point. All I know is his last name is Scott. And he took a hammer and a feather with him to the moon. And he performed the exact same demonstration in the in the zero atmosphere environment of the moon, and got the result that you would expect if you believe that all things should fall with the same rate regardless of how massive they are. Before you move on to those video demonstrations and convince yourself that all things fall at the same rate, let's just take another look at all of our kinematics equations. So we'll say we have some equations for motion in one dimension on a horizontal or x axis. And we say delta x is equal to 1/2 v naught plus v times t, or v equals v naught plus at. How about delta x equals v naught t plus 1/2 at squared? Or why not v squared equals v naught squared plus 2a delta x? Well, in free fall, we're going to save it for future chapters, this discussion about satellites in orbit. Or I think it'll be in our very next chapter that we'll talk about projectiles moving in 2 dimensions. For now, we'll restrict ourselves to motion in 1 dimension, but what if we drop something or throw something straight up or down vertically into the air? Then we can study motion in 1 dimension on a vertical axis or on the y-axis. So that just changes the equations ever so slightly, and we get delta y equals 1/2 v naught plus v times t, v equals v naught plus at, delta y equals v naught t plus 1/2 at squared, and v squared equals v naught squared plus 2a delta y. So we probably don't really even have to write it out as a separate list of equations. Just know that there's more than one symbol for displacement. When things displace along the horizontal axis, we use x, and vertical, we use y. But they're the same equations, of course. And in our study of one-dimensional motion on a vertical axis, we're going to limit our study to motion on a vertical axis that's a result of the influence of gravity or free fall. So we can even erase wherever there's a symbol A, any equation that has acceleration built into it. When free fall is the resulting motion, then that acceleration is the acceleration due to gravity. And so we'll use the symbol G. And now when we make our list of known and unknowns, the problem won't have to go out of its way to describe what the acceleration is. For example, there could be a problem that says an object is dropped from a height of 20 meters. How much time will it spend before it hits the ground? So make a list of all the kinematics quantities: displacement, time, acceleration, initial velocity, final velocity. There's always 5 quantities to look for in a problem of this sort. So we were told that the object was released from a height of 20 meters. We're asked for the amount of time it spends in the air. If it's dropped from a state of rest, we know the initial velocity was 0. The question I asked wasn't how fast will it be going when it hits the ground. The question was how much time will it take to hit the ground. I didn't tell you the acceleration because I didn't have to. We can assume it's acceleration due to gravity, and so the numerical value we know is 9.8 meters per second squared. So the equation that doesn't include final velocity, well, it's not that one, it's not that one, and it's not that one. This is the equation we would want. And if the initial velocity happens to be 0, this equation simplifies to delta y equals 1/2 gt squared. And in fact, this was the same equation that you used in the experiment on determining your reaction time by dropping a ruler through your fingers. So when we rearrange this equation to solve for time, we get time is the square root of 2 times the displacement divided by g. Notice I didn't use the symbol delta y, I just used the symbol y, and that's because I'm assuming that the initial position where the object was released from is the origin. So t equals the square root of 2y over g. I'm going to guess that this is a formula that will appear over and over and over again throughout your study of physics. So in any case, we can plug in the numerical values and see what we get. This is square root of 2 times 20 meters divided by 9.8 meters per second squared. The meters cancel out. Now we have 1 over the inverse of square seconds, which is just as good as having square seconds. Oh, but we're taking the square root of all this. So indeed, this is a good equation to use to solve for an amount of time because we're getting seconds as the units. If you reach for a calculator and figure out what is 40 divided by 9.8, take the square root, this is very nearly 2 seconds. In fact, it's a common approach in the study of free fall just to round up and say acceleration due to gravity is equal to 2 sig figs is equal to 9.8 meters per second squared. So that's approximately the same as 10 meters per second squared. In fact, if all you care about is getting an answer to only 1 sig fig, that is the acceleration due to gravity, right? To 1 sig fig, acceleration due to gravity is 10 meters per second squared. And then in that case, the numbers would have been 2 times 20 over 10, which would give exactly the square root of 4, which would give exactly 2 seconds. So if you don't mind being off by a small amount or not maintaining a large number of sig figs and just want to get a quick, reasonable answer, then it's fair to round up the acceleration due to gravity to 10 because that'll often make the math a little bit simpler.